Alright, y'all, here we go. Let's talk about linear approximation. Some call this the Newton-Raphson method. I think it was published something in like 1669 by Newton, and then Raphson also published with this the better version of this that we're actually using. So Newton-Raphson, I don't know. Whatever. So, Newton's really weird, though. If you just, look up how weird he was super weird. If you were asked to find the average rate of change, what would you do? I think if you were looking for the average rate of change, then you're just looking at a delta y over a delta x. So that's the slope, and that's the change in the y, so y minus y1, over x minus x1, where x1 and y1 are just some numbers that you have. Cool. So, let's get a little bit of vocabulary happening. So, given a function, you have differentials of dy and dx. These are differentials. And their relationship is a rearrangement of dy dx equals f prime of x. So just separating a little bit our understanding of our notation, where yes, this is true, but we can also, these are numbers because a derivative is still a number, so then we get a change in y divided by a change in x. These are changes that are happening. So we can write our differential in terms of our function as well, so it doesn't have to be dy dx, it can be df dx is f prime of x. So then when we rearrange this, we get this form right there. So let's look at this example where we're computing dy, which is our differential, and our change in y for this function where we have cosine of x squared plus 1 all minus x as our x value changes from this 2 to 2.03. So this is a calculator kind of problem. So well, the change in y, that one's pretty straightforward, because all you need to do is just plug in some numbers. So the change in the y value is going to come from when we're looking at cosine of 2.03 squared plus 1 minus 2.03 minus, and then I'm going to put parentheses because that's responsible, and then I'm plugging in 2. Right, I'm going to plug in the 2. So then I get, cosine of 2 squared plus 1 minus 2. And when I do that calculation, I get something like 0.084 or something like that. For our AP exam stuff, we do need thousandth place precision. For other things in life, you probably need more, especially since we have computers that can handle a lot. All right. So that's the change in y. What about our differential? So our differential, that requires us to take our derivative of y. So let's just take dy dx and look at that. So that is, with the chain rule, we have our outside function is cosine, so the derivative of that is negative sine of x squared plus 1, but now I need to take the chain rule, so I take the derivative of the inside function, and that is a 2x. And then just this minus x, when I take the derivative, the slope of that is 1. So I have dy dx is negative sine of x squared plus 1 times 2x minus 1. So now, to get my differential, I need dy equals negative sine x squared plus 1 times 2x. So I'm going to put the 2x there in the front just because why not? And all of this, we are dxing, multiplying by our change in our x. So from here we need to look at what this change is. So the dx is the difference between these two, which is 0.03. So I have dy, poor board management, dy is going to be negative 2, and then what x value am I plugging in? I'm actually plugging in my original, the first one that I knew, which is 2. And that's unfortunate that those are both 2's. And then I have sine of 2 squared plus 1 minus 1. And all of this I'm multiplying by my change in my my differential of x, which is 0.03. Okay, and then when you like calculator that, then you get like 0.085, which like these are pretty close. So like that's nice that our change in y that we calculated is only 1,000th off from our differential. But some other times, you know, that really might not be the case. So let's look at some good ways of using this idea, this connection of the slope with maybe finding approximations when we have small changes to try to figure out what an actual value might be just by using some lines. So a way that we're going to try to think about that is by using actually this like rearrangement of the slope formula. So this is our iterative method because we have x sub n plus 1. This is a subscript. I think if you're typing things, then if you do an underscore, then you should be able to get a subscript. You might need a curly bracket to get a multiple things in your subscript. But that aside, we have x sub n is an approximation of a solution of our f of x equals 0, which solutions are whenever our function equals 0. That's one of those things where there's the zeros, the number of them is the same as the exponent of your highest power. This is the fundamental theorem of algebra, that the number of like solutions that we have is equal to the highest power or the degree of our polynomial. This is ER. There's roots. So zeros are roots. 0 equals the factors, factored form. And that's a way that we can find these zeros or these roots. Zeros and solutions. So in general, when we're talking about solutions, we're looking for the zeros, which are the roots, which we find by taking 0 and setting it equal to the factored form, and the number of those that we find is based on the exponent because that is the fundamental theorem of algebra. And look, it spells zeros. That's so fun. Wow. So where was I? So when we're looking at f of x equals 0, and our derivative at our initial approximation of our solution is not equal to 0. So we don't have a vertical tangent line, right? Because we don't have a horizontal tangent line. Our derivative is not going to be just like a slope of 0. There's no chain. Then we can find our next approximation, which is x sub n plus 1. That's our next term. Or our next approximation of our solution by taking our original approximation and then subtracting our function evaluated at that point and our derivative evaluated at that point. And let's just play with a little bit of the algebra here. So when we have let's look at if we move this around. So if we get x sub n plus 1, and then this is minus x sub n. This equals negative f of x sub n over f prime of x sub n. And, well, I can negate everything, right? So I can just negate like that. So let's rearrange. So I have x sub n minus x sub n plus 1 because of the commutative property of addition. And this is addition now, so that's nice. Addition, boom, right there. This equals, I'm going to move over here because my head's in the way, f of x sub n over f prime of x sub n. F of x sub n, this is a y value. And this is a slope, right? So if we rearrange that just a little bit, then we have f of x sub n equals our slope evaluated at x sub n times x sub n minus x sub n plus 1. And this is the equation of a line, because we have a slope here that's a number, right? Because our derivative is a number, and that's times x minus x sub n plus 1. So this is a known value, and then this is our next thing that we don't know yet, and this is a number. This is a y value. So x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n is how we find some approximations for our solution of a given function. This only works when our derivative of our function is not 0, because if you have a slope that's 0 and you're trying to divide by 0 here, it's not going to work. Or if you're just looking, you're just going to get this f of x sub n equals 0, and that just doesn't really help you. Or you already found your solution. So we need to use Newton's method to determine, or Newton-Raphson, to determine an approximation to the solution cosine of x equals x that lies on the interval from 0 to 2, and we need to find an approximation to 3 decimal places. So let's take our initial guess at x equals 1. So I'll let you try to work on that, and I'll just put a question here to see if you can get the right answer, and then we'll walk through it. All right, so first things first, we don't have a function that equals 0. So when will cosine of x equal x? Well, that's when cosine of x minus x equals 0, right? We just move the x over to the other side. So we have our function f of x now is cosine of x minus x. So if our initial guess, so let's call that x sub 1, or x naught, that's initial, x naught, N-A-U-G-H-T, that's a little Britishy for you, but x0 if you want to be American about it. X naught is 1, so that means that x sub 1, other people say, is x naught minus f of x naught over f prime. So I know that I have f of x, but I don't have f prime, so let's take the derivative. And the derivative of cosine is negative sine of x, and my derivative of negative x is negative 1. So all I need to do is just plug in what I have. So I have x sub 1 equals 1 minus f of f of 1 is cosine of 1 minus 1 all over negative sine of 1 minus 1. And then I plug that in and I get some number, and it's like 0.75 something, 0.4 stuff. Okay. So we need our approximation to 3 decimal places, and we need it to be accurate to 3 decimal places. So this is our second guess, and it is very different from our first guess. This is like 0.25 stuff away, well, a little bit less than 0.25 away from our initial guess. So we have not yet gotten a good approximation. So what should we do? We should do it again. So let's find x2. So x sub 2 is x sub 1 minus f of x sub 1 over f prime of x sub 1. And then we plug in stuff and we evaluate, but actually I don't want to do that by hand. So let's look at a Google Sheet. So in our Google Sheet, we have our initial guess. So this is x sub, well, it's bad labeling, sorry, x naught, and then this equals this one plus 1, so then I have the step counter as I click and drag this down. Okay, so I have my x naught, so then I plug that in to my f of x, which is cosine of that cell minus that cell again, and my f prime is negative sine of x minus 1. So I called this cell again as B2. And then I got b2, which is the x naught, minus c2, which is f of x naught, over d2, which is f prime at x naught. So that is the value that I got. Okay, cool, right? That's what we got. And then now we need to evaluate. So I just got that by taking this cell, taking that little thingy and dragging it down, and then I got a new point. Well, that's pretty nice. I got a new f value, and then I took the derivative and I dragged that formula down, and then I got negative sign of my x1, and then in order to get my x2, I'm going to copy that down, and look, these are less different, so that's good. And I'm going to copy down this formula to see, oh, and now my function evaluated there is very close to 0. It's approaching 0 from below, and my slope is pretty close, and that makes sense because I'm evaluating at a very close point. So let's find our next step. Let's iterate. This is the Rafsini part, the iteration. And look, now we have consistency. We have 0.739 in both of these, so we have accuracy to the thousandth place, and so we're done. We have an approximation of our 0, or our solution, for our function cosine of x minus x, and a 0 for that, or cosine of x would equal x, approximately at 0.73. And you could do more steps if you wanted to, just by taking that and dragging it down. And actually, I think we get like a very nice. Yeah, look at that. We get our actual 0, and that's only a little bit away. It's like many, I don't know. It's a very small difference, but then then we got it. Pretty cool. All right, let's try this. How are we gonna find an approximation to the solution of cube root of x equals 0? And remember, the cube root function looks something like that. That's really poorly drawn. Sorry about that. But it's interesting to think about because this is the inverse of x cubed, right? So then what's happening here? Where is our function going to be equal to 0? It's going to be at the point 0, 0, right? Because this is the inverse. The inverse of this function is x cubed. And x cubed, like if you plug in 0, you get out 0. So the inverse of it is also going to have a root of 0, or cube root of 0 is 0. But what if we use a really bad approximation? What if we choose 1 as our first guess? Let's see what happens. So if we have x naught equals 1, then I have x1 is x naught minus f of x naught over f prime of x naught. And oh, I didn't take my derivative because I have f of x is the cube root of x, which I'm going to write as a power to the rational exponent, just because I feel like that's easier to work with. So we have f of x equals x to the 1/3 power, which means f prime of x, because of the power rule, is 1/3 x to the negative 2/3 power. So if we have negative 2/3 power here, then what do we get? We get x1 equals 1 minus f of 1, which is 1 to the 1/3 power, divided by 1/3 x to the negative 2/3 power, which is just 1. So then I get x sub 1 is 1 minus 3. 1 minus 3 is negative 2, which is an even worse guess than what we were doing before. So let's look at the picture to see why that's happening. Let's see. So this tangent line is happening at the point 1, 1, and the slope here is 1/3. So we have 1/3 is our slope. So the equation for the tangent line is y minus 1 equals 1/3 x minus 1, yes? So let's plug that into a graph. So what did we say? That was y minus 1 equals 1/3 x minus 1. like that. Let's just make sure that that is a tangent line to our curve. So what was our curve? It was nth root, third root. Yeah, so we got a tangent line right there, right? And look, this is where the 0 that we found was. So now, if we figure out what our tangent line is at this point, what are we gonna get? Well, let's do it. Tangent line for x sub 2 is gonna be -2 minus f of -2 over f prime at -2. And what is that going to be? That's -2 minus f of -2, so -2 to the 1/3 power over 1/3, and then -2 to the -2/3 power, and then because these are like the same base, right, we can like do some math, so it's -2 minus, because this can go with that in the numerator because they have the same base, so that's a +6. So then we get +4, which means that we have a super wonky line. Our line is going to give us, because we have the point -2 comma -2 to the 1/3 power, and our slope is 1/3 times -2 to the 2/3. Oh wait, what is that? That can go up in the numerator, so that's what. No, that's in the denominator. Okay, so that's -2 to the 2/3 power, and so we have y minus plus 2 to the 1/3 power equals 1/3 negative out here. No, not negative, it's positive. Because this is a squared, so that's 2 to the 2/3 power times x plus 2. Let's plug that in and see what happens. So looking at this graph here, we have the tangent line, which got us our approximation of -2, so then this is our tangent line at -2, and it gets us 4. So we're actually getting farther away, because remember our initial guess was that x equals 1, and so this is super unhelpful. So sometimes the Newton-Raphson method for linearization of just finding roots totally fails, and that's okay. Alright, so let's do this one last example. We need to use Newton-Raphson's method to determine x sub 2 for the given function and the given value of x naught. So our initial guess here is x naught equals 5. And we have this like this cube thingy. So let's take our derivative. And so this is just a pretty straightforward power rule, which is pretty nice. We got 3x squared minus 14x plus 8. And then the derivative of -3 is just -0, so we don't have to do anything there. It's really nice. These problems are from Paul's online notes, which I highly recommend that you use as a supplement for our class notes. He just has really good explanations. So Paul's online notes, shameless plug. This is definitely how I got through a lot of my math classes in college, so recommend. So we have f prime is this, and we have f of x, and we have x naught. So x1 equals x naught, which is 5, minus f of 5 over f prime at 5. Let's do some math, I guess. So what is this? 5 minus 5 cubed is like 225, minus 7 times 5 squared is 7 times, it's like 8 times 25, but then minus 1, so there's that. 375? That might be wrong. That's okay. Arithmetic is difficult. and then plus 40 minus 3 all over f prime at 5, which is 3 times 25, 75, minus 14 times 5, which is like 70, and then plus 8. I hope that that is all right. And so what do we get? 6, I think. I'm looking at Paul's online notes right now, but I think it's supposed to be 6. Maybe something's wrong here. I don't know. So so we got our x1, that's 6. And I really don't feel like doing the writing it out for the other one. So x sub 2, you do that on your own, and then I'll put a question here, and then we'll see if you get it. All right, so I'm finding that x sub 2 is 5.71875. If you just plug in 6 to this formula that you have, 6 minus f of 6 over f prime at 6. So x sub 2 is that. And I think that'll about do it. I hope that helps, and we'll talk more about doing these kinds of problems in class.